So now, to better understand what we have studied, let us try to apply it in a sample problem. So this is the sample problem. A pretensioned pre-stress beam has a span of 15.2 meters or 50 feet as shown. So this is the uh, pretension beam. It has a tendon profile uh, like this. So it is a harp tendon profile. So this is the pretension beam, and it is just a simply supported beam which carries a uniformly distributed load W. Calculate the concrete fiber stress or stresses uh, at transfer at the centroid of the tendon for the midspan section of the beam. So we are concerned on the concrete fiber stress located at the centroid of the tendon at midspan. So we want to find the fiber stress acting on this particular location at midspan of the beam. And then after that, calculate also the magnitude of loss in prestress due to the effect of elastic shortening of the concrete. Assume that prior to transfer, the jacking force on the tendon was 75% of the ultimate strength of the prestressing reinforcement. So other details about the given pretension beam, if you will look on the cross-section at midspan, it will look like this with dimensions given. So the depth of the beam is equal to 762 mm or 30 inches. The width is equal to 381 mm or 15 inches. And then the distance from the bottom of the location of the tendon or the pre-stressing reinforcement at midspan, which is this, the location with respect to the bottom is equal to 101.6 mm or 4 inches. And then the 28 compressive strength of the concrete, FC prime, is equal to 41.4 megapascal or 6,000 psi. The initial compressive strength of the concrete at transfer is equal to 31 megapascal or 4,500 psi. The ultimate strength of the pre-stressing reinforcement equal to 1,862 megapascal or 270,000 psi. And the area of the pre-stressing reinforcement is equal to the area of a 1/2 inch diameter 7-wire strand, which has an area equal to 99 mm squared or 0.153 inches squared. So we have 10 of those 99 mm squared 7-wire strand used as a pre-stressing reinforcement here on this particular problem. And then the modulus of elasticity of the pre-stressing reinforcement equal to 186,200 megapascal or 27 times 10 to the 6 psi. So let's start to address the first question, which is the concrete fiber stress at transfer located at the centroid of the pre-stressing reinforcement at midspan, which is this. So since we are already at transfer stage with self-weight, obviously, if we want to find the concrete stress acting at this particular location, located at midspan, we can use this formula that we have shown a while ago. So again, this is just similar to the formula for finding the stresses on the pretension zone, which is the zone which is initially experiences tension as the concrete beam supports its own weight. So this is the pretension zone, the lower portion of the concrete beam with respect to the neutral axis or centroid. And since the stress we are concerned is located here, same location as the pre-stressing reinforcement at midspan, we just have to uh, replace C here, the distance from the centroid or neutral axis to the fiber that we are concerned to find the flexural stress, we just have to replace that magnitude C with E, since the distance of the fiber we are considering with respect to the neutral axis or centroid is at a distance E from the neutral axis or the centroid. So we just have to replace it by E. So in this equation, AC, we can already compute for AC. We have a given cross-sectional dimensions. We can also find the moment of inertia of this particular section because the dimensions are given. The E, I think we can compute for E because we are given with this distance from the bottom of the pre-stress reinforcement. So the only unknown uh, parameters here in order for us to compute the concrete stress acting here at the location of the pre-stress reinforcement at midspan are the value of P and M. And how can we solve for the value of P? If you can remember, P is the pre-stressing force that was transferred to the concrete element when you cut the pre-stressing reinforcement after jacking. So how can we get that magnitude of pre-stressing force that was transferred to the concrete after the pre-stressing reinforcement was cut after jacking? So if you can remember, the formula that we have given before a while ago is this. This is the magnitude of the actual force that is actually transferred to the concrete element as you cut the pre-stressing reinforcement. So again, it is not equal to the jacking force itself because the pre-stressing reinforcement experiences relaxation during jacking, which causes a pre-stress loss equal to this magnitude. Although since we are not given with this particular magnitude, the magnitude of the magnitude of the relaxation as well as the jacking force. I mean the pre-stress loss due to relaxation is not given, although it is given on the problem or mentioned in the problem that we can assume that before transfer, the jacking force or simply the force acting on the pre-stressing reinforcement is equal to 75% of the ultimate strength of the pre-stressing reinforcement. So therefore, with that mentioned, we can say that the magnitude of P, which is again the force that was being transferred or was transferred to the concrete element after the uh, pre-stressing reinforcement was cut, or therefore before the actual transfer. The magnitude of that, as mentioned in the problem, we can assume that it is just equal to 75% of the ultimate strength of the pre-stressing reinforcement. Although we are concerned with force, so we have to convert this stress. This is just a stress. Take note. This is just a stress. So we just have to convert it to its corresponding force. So again, from strength of materials or mechanics of the formable bodies, stress is just equal to uh, force over area, or simply force is just equal to stress times the area. And since we are given with these parameters here, we just have to substitute the magnitude of FPU, which is this 1862, and APS 1099 mm squared 7-wire strand. And then for uh, for the sake of to have a better units, we just have to convert the resulting value here, which will be in terms of Newton, to kilonewton. So we just have to divide it by 1000 so that the resulting answer will be in terms of kilonewton. So that's the magnitude of P. So now we will now be concerned with the M here, which is again a transfer with self-weight. We know that the M here on the formula is just equal to the moment due to the dead load or self-weight itself. But the problem here is there is no dead load or self-weight given, or there is a self-weight given. Actually, there is no self-weight, magnitude of self-weight or dead load directly given, but we know that if you want to find the weight of a concrete in terms of a uniformly distributed load, we can just multiply its unit weight by the cross-sectional area. We know that. We know that for a fact, even before on our previous courses that we have taken. If we want to find the weight of the concrete, which has a unit weight equal to 23.54 kilonewton per cubic meter, we just have to multiply that unit weight to the cross-sectional area to find the weight of the concrete per meter or per length. And knowing that, uh, if we want to find the particular magnitude of the moment acting at midspan due to that uniformly distributed load or simply due to that self-weight, we know for a fact that the magnitude of the moment acting at midspan is just equal to WL squared over 8, wherein W is equal to the magnitude of the uniformly distributed load, and the L is the length of the beam, which is equal to 15.2 meters as given on the problem. So we just have to substitute all of those parameters on this particular formula. So the unit weight, so this is the weight of the concrete in terms of force per length. This is 23.54 kilonewton per cubic meter, and this is the cross-sectional area of the concrete. L is the length, again 15.2 meters. So if we will substitute all of the parameters needed, this is 23.54 kilonewton per cubic meter. This is the area of the cross-sectional section. Cross-sectional, this is the area of the cross-section of the concrete element, the product of the base or the width and the height. But you just have to take note of the consistency of units because this is in terms of kilonewton per cubic meter. So this must be in terms of meters. So we have to convert both mm into meters. So we have to multiply this by, or we have to divide this by 1000 as well as this. Or if we will incorporate them together, we just have to multiply the whole expression here by 10 to the negative 6. And then L is equal to 15.2. So we just have to square that divided by 8, the whole product. Then we will find the um, bending moment acting at midspan due to the dead load or self-weight of the concrete beam, which is equal to this. So the resulting units will be equal to kilonewton per meter, since we have expressed this in terms of kilonewton per cubic meter and the other parameters in terms of meter. So last thing that we need is the E, the magnitude of E. And again, take note, E is the distance between the centroid or the neutral axis to the location of the pre-stressing reinforcement. So if we are given with the distance of the pre-stressing reinforcement with respect to the bottom, and since we know that this is just a rectangle which has a centroid or neutral axis equal to the half of the height, therefore we can readily compute for the eccentricity E, which is just equal to the half of the height, which is 762 divided by 2, minus the distance from the bottom of the pre-stressing reinforcement, which will result to this. So this is the eccentricity of the pre-stressing reinforcement. So there, since we already uh, found the parameters needed to solve for the fiber stress acting at the concrete uh, on the location of the centroid of the pre-stress reinforcement at midspan, therefore we can already compute for it by just substituting them on this equation. So again, P is equal to this. Although for consistency of units, in this particular formula, we just have to convert all of the forces in terms of Newton, area, mm squared, moment of inertia, mm to the fourth, distances such as E equal to mm, and then the bending moments, we just have to express it in terms of Newton per mm, Newton mm, so that the resulting stress that we will find here will be expressed as in terms of Newton per mm squared or equal to megapascal. So the force again is equal to this. Area, just have to multiply the width and the height. And then the E, we already computed it. Moment of inertia of a rectangular section is equal to B h cubed divided by 12. And then the given or the computed bending moment due to the dead load equal to this. So again, the 10 to the 6 is just the conversion factor to Newton mm. And then if you will try to solve this, we will find that the stress acting on the concrete on the location of the pre-stressing reinforcement at midspan is equal to this, negative 8.519 megapascal. And since it is negative, therefore, it is a compressive stress. So that is the first thing that the question asks. So if you can notice, at this particular stage, a transfer with self-weight, the stress acting below the neutral axis or the centroid at this particular stage of pre-stressing is still a compressive force. So therefore, at this particular stage, you can imagine that the concrete beam is still bended upward. It still experiences camber. That's why the fiber stress being experienced below the neutral axis or the centroid is a compressive stress, as shown here, as computed here. So this is the concrete fiber stress acting on the same location of the pre-stressing reinforcement at midspan. So if we will try to address the second requirement here on the question, which is the magnitude of the loss of pre-stress due to the effect of elastic shortening of the concrete, actually we can use this particular information here that we have computed. Because if you can remember, if you can recall, the formula for finding the pre-stress loss due to elastic shortening of concrete is equal to this, wherein the E is the modulus of elasticity of the pre-stressing reinforcement, FCS is this, the stress acting on the concrete on the same level of the pre-stressing reinforcement, and then ECI is the modulus of elasticity of concrete at transfer. So again, I will repeat again and again. The modulus of elasticity is dependent on compressive strength of the concrete. And since at transfer stage, we know for a fact that the concrete is yet to attain its 28-day compressive strength. Therefore, the compressive strength at transfer of the compressive strength of the concrete at transfer is still less than the 28-day compressive strength, which is this. So if that is the case, since modulus of elasticity is dependent on compressive strength, therefore we can expect that the modulus of elasticity at transfer will have a different value as the modulus of elasticity of concrete at after it already attained its compressive strength, its 28 compressive strength. So EPS is already given on the problem. FCS already computed. The only unknown here on this particular equation is ECI, the modulus of elasticity of concrete at transfer, the initial modulus of elasticity. And how can we compute for that value here? So if you can recall, if you will try to look at, if you will try to recall the code provision of ACI 318M-14, specifically on section 19.2.2.1, it is specified here or there how to compute the modulus of elasticity of a concrete. Although in this particular problem, since we don't know if what type of concrete was used, we can always assume that the concrete used is always a normal weight concrete. So we can use this formula. If we will refer to ACI 318M-14, or if you will refer to our local code NSCP, you can see similar formula. So that is how we can compute for the modulus of elasticity of concrete. If we want to compute the modulus of elasticity of concrete, a transfer, therefore, the FC prime that we have to use here must not be the FC prime, the 28 compressive strength, but the FCI prime, which is equal to 31 megapascal. So substituting all of those values, EPS, FCS. So you just have to disregard the sign, obviously, because we know for a fact that the sign just indicates whether the stress is whether the stress is compressive or tensile stress. So you just have to disregard it. Divided by ECI, which is equal to this 4,700 square root of, again, not FC prime, but FCI prime, which is 31 megapascal. So if you will try to compute that, you will get this magnitude. So this is actually the expected prestress loss that will be experienced by the prestressing reinforcement due to the elastic shortening of the concrete. And again, we know that the concrete shortens because the compressive force from the prestressing reinforcement after jacking, immediately after the prestressing reinforcements are cut, were transferred to the concrete element. So that is the reason why the concrete element experiences elastic shortening because of that prestressing force transferred to it by the prestressing reinforcement after the prestressing reinforcements are cut. So that will be the expected magnitude of the loss of prestress due to the elastic shortening of the concrete. And again, we know that uh, the prestressing reinforcement loses prestress because as the concrete as well as the prestressing reinforcement shortens, the prestressing reinforcement tends to lose some of its prestressing force that it carries. So that is why we that is why the prestressing reinforcement experiences this magnitude of prestress loss again due to elastic shortening of concrete.